Okay. Oops. Okay. So this right here is the smallest separation that you can have for the objects to be distinguishable. This right here is the distance of the object, and this right here is the angle, and this is measured in radians. Now, what you also have to do is on this theta sub r, this is 1.22 times lambda, the wavelength, and this right here is the diameter of the aperture, right? So this is going to be the diameter of the pupil of your eye in this particular instance. So if we take this value right here and substitute it into this equation, it becomes 1.22 times the distance to Mars times the wavelength divided by the aperture of your eye. So it's 1.22. The distance to Mars is 8 times 10 to the 10th meters. This right here, wavelength is 500 times 10 to the minus 9th meters. And then their aperture is 5.0 times 10 to the minus 3rd meters. So all of them are in meters here, which gives you 1.1 times 10 to the 7th meters, or 1.1 times 10 to the 4th kilometers, right? Now, if you look at your table, you'll see that this distance is greater than the diameter of Mars, so you can't, with your naked eye, you can't make out any specific thing on Mars. Now, if you use the telescope, and instead of having 5.0 times 10 to the minus 3rd meters, if it's 5.1 meter, that same equation becomes 1.1 times 10 to the 4th meters, or 11 kilometers. And of course, Mars' surface is much larger than this, so you can make out quite a few details on Mars with from the observatory. Now we're going to go on to diffraction by a double slit. So waves passing through two slits produce a combination of double slit interference and diffraction, right? So the intensity to be expected, so you have a whole lot more here, so that you have a general band, right? And then you have this one right here. So what you're going to see is this overall band right here is the minimum for the first one. So this would be your first minimum. And the fact that you've got a second one there, you just have all these different individual peaks there, right? So by having double slit, you have vanishing narrow slits, and the intensity spot diffraction is typically as it is shown here, right? The intensity plot is expected for a 2-width slit is shown right here, okay? So this right here gives the envelope for it, and the diffraction minimum eliminates some of the double slit fringes, and then here's your first maximum beyond your 0th order maximum here. So that is the way in which you have to interpret these particular ones. So for identical slits with a width A and a center-to-center separation distance, so this is how the opening itself is this size. This is the distance between those two slits. The intensity pattern is given with the angle theta for the central axis as this right here. The intensity, we have this value right here. Now we have this value as well in there, okay? Where beta is pi d, which is the separation of the slits, times lambda sine theta. And then alpha still includes the slit width measurement over lambda sine theta, okay? So this is the distance between the slits. This is the width of the slit, okay? So note carefully that the right side of the double slit equation is the product of two factors. The interference factor is due to the interference between the two slits, and the diffraction factor is due to the diffraction by a single slit of width A. So the two different factors involved here when you have a double slit. So in a double slit experiment, the slit separation D is 2 times the slit width, W. How many bright interference fringes are in the central diffraction envelope? Okay, and this is problem number 37 in your book. So D is going to equal 2W, right? So when you have this equation right here, A sine theta is where this is 1, and just converts into this equation right here, right? D sine theta over A sine theta over D over A, which is 2W over W, or just simply 2. So when you've got a slit separation that's 2 times the slit width, what that means is your minimum occurs at twice that value. So 2M2 minus 1 is 2D over A minus 1, 2W over 4. So it's 4 minus 4. So that answer is 3 for this value right here, right? Again, how many bright interference fringes are there in the central diffraction envelope? And the answer is 3. That means what you're doing is you're going back here and saying, how many of these do you encounter before you get to this first minimum? And what what you're calculating there is showing that there are 3 of those different ones. This is practical exercise number 8, problem number 39. Light of wavelength 440 nanometers passes through a double slit, yielding the diffraction pattern that you see here. This is the intensity here. This is the angular position. This right here is 5 degrees right here. This is 2.5 here. Okay, and so your first, you've got 1, 2, 3 before you get to this first minimum at 5 degrees. And from this, they want you to calculate the slit width, the slit separation, and verify the displayed intensities of M1 and M2 interference. In other words, whoops, good grief. Okay, they want you to calculate these intensity values. Now, the first minimum is at 5 degrees, okay? So it means A equals lambda over sine theta, 0.440 microns, divided by sine 5 degrees, 5.50 microns, right? That's the first minimum. So for this value here, for this wavelength, this is going to be the value of A. Okay? And that's because this occurs at 5 degrees right here. Now the fourth bright fringe is missing, right? So D equals 4A. It's 4 times this right here. So what you're doing is you're going back and you're seeing which you've got 1, 2, 3. The fourth one is missing. So that is the reason why you use D as 4A. Okay? So 4 times 5.0 right here gives you what the separation is between the slits. So you count the number of slits, right? Multiply that number. I'm sorry, you calculate the number of ones that you have here, whichever one is missing. That is an integer that you use to calculate times the width of the slit to give you the distance between the different slits. And for the third part, you now have your A value, you've got your D value, and you can calculate alpha. Okay, so alpha is A pi sine theta over lambda, and so this is where your A value goes in. Sine 1.25 degrees. This is your wavelength. This gives you the radians values for alpha, 0.787. So the intensity of the first fringe is going to be IIM sine alpha over alpha, right? And so what you looking back at the graph here, this right here, the I0 is at 7. So what you're doing is 7 milliwatts per square centimeter. Sine of this in radians divided by 0.787 radians, okay, alpha, is 0.57 milliwatts per centimeter squared. For M2, you would have this value right here, okay? It would be 2 times that to give you this value, okay? So you have 7, and that's milliwatts per centimeter. Sine 1.574 divided by 1.574 squared. And this gives you 2.9. Going back to this figure, you'll see that this right here is what? This is about 5.8 or so. This right here is about almost exactly 3. Okay, so 5.7 and 2.9. I calculated mine out, and I actually got I got a little closer to 3 there. But anyway, be that as it may, that's shows that when you calculate the n values and that from that type of a diffraction pattern, calculating the slit width and slit separation allows you to determine exactly the height, the intensity of these different ones. Okay, next under diffraction gratings. The diffraction grating is a series of slits, okay, instead of just 2 of them. And so you've got your individual D's between them. You've got your individual A's for each one. So this is right here as 5 different ones. And for these, d sine theta equals m lambda. Okay, this is a diffraction by multiple slits, has this type of an equation, where you're now looking at the distance between these instead of the a value here for this, right? Whoops. And the line's half width is the angle from its center to the point where it disappears into the darkness. That's the half width. And that's given by delta theta, half width, that's what the HW stands for, lambda, n, d cosine theta. Okay, the half width of the line at theta. Okay, so that this is the number of rulings, n, in case you, this right here would be 5. Okay, it's possible to have more than that. D gives you the distance between those. This is your cosine of theta. Okay, and thus, so for 2 diffraction gratings, the grating with a larger value of n is better able to distinguish between wavelengths because its diffraction lines are narrower and less likely to overlap. Okay, that's a key fact of how these things work. Practical exercise number 9. This is problem number 46. Here you've got visible light incident on a grating 315 rulings per millimeter. So this is your n value, right? The longest, what's the longest wavelength that can be seen in the 5th order diffraction? Okay. So the mth order, that's going to be 5 lambda. So sine theta for m equal to 5. There should be an equal sign there. By the way, this is 1 millimeter. It's not 1 nanometer. Okay, it's 1 millimeter. And so, and what you have to do is you set it with a less than. So 5 lambda over d less than 1. So d is your distance between them, which is 1 millimeters divided by 315, which is your n value, and you're looking for your 5th one, so that is 5. Okay? So that's 600